Where did all those black holes come from? Were there primordial black holes? Did they all have to come from the stars? These are now profound new questions that have arisen. These questions can be answered by gravitational wave research.
If you look at all the different engineering solutions that went into LIGO and all the tricks and great ideas that got it to work, what is the one that you're most proud of or you think is the most interesting?
You'll laugh at this. Everybody thinks that the position sensitivity that we got, the ability to measure 10 to the minus 18 meters. And yes, that's an accomplishment, no doubt. But once you analyze the instrument and you go along, you can do that, it turns out. And I think now we can go further because of the understanding of the quantum noise. I was involved in something which was very much ordinary, but could have failed, and it didn't. And that was one of the things we knew we had to do. Is in order to make 4 kilometers of vacuum, 4 kilometers vacuum at, call it 10 to the minus 9 torr, or even 10 to the minus 10 torr, at what is called ultra high vacuum. I thought that was an engineering task that we took on, and we won a big gamble. A lot of people thought we would never be able to do it at the cost that we did. And the same thing is going to happen now with the next version of LIGO, which is we hope to make longer. We hope to make a 40 kilometer long LIGO arms in the next version, because we now know what sensitivity you really need. Having measured all these sources, we know we didn't make LIGO long enough. If we want to get into cosmology, near-term cosmology, for example, where did all those black holes come from? Or what star, were there primordial black holes? Did they all have to come from the stars? These are now profound new questions that have arisen. Or what was the first stars that were made? What were they made of? We think they were made of hydrogen. They most certainly were made of hydrogen, but how long did it take for the very first stars to form? And that's something that James Webb will tell a little about, that new telescope. But anyway, these questions can be answered also by gravitational wave research if we make this thing 10 times more sensitive. I don't think there's any point in making it more than that sensitive on the ground. But that extra factor of 10 will get us into what I would call the beginnings of it's the end of the early moment of the universe and the beginning of what's really astronomy. It takes us to a mega year after the explosion. The cosmic background takes you to about 300,000 years after the explosion. This will take us to about and unless there's stronger sources still. That's something we're pushing in the United States. It's called Cosmic Explorer. And that, of course, is the next thing. And I think it's a very realistic thing. And that has the same problem. How do you make the vacuum system cheaper so that you can afford it? And for LIGO, what that did is we made something that which, of course, normally would have cost, it cost about $50 million. And with all the innovations we made, it would have cost 6 times that, 300 million. It would have completely wiped out the planet if we hadn't learned how to make a cheaper vacuum system. That was an engineering challenge. You asked for an engineering challenge. That was it. There were a lot of tricks involved. The most important one is that you could learn how to get rid of all the things that made gas by doing cheaper things. You could bake hydrogen out of the steel. You could, with a low temperature bake, could get rid of the water. And so consequently, you didn't have to pump. You had a very big diameter, very different. See, an accelerator is like this. You have to have many pumps. We were able to get away because we thought it through carefully, that we had only pumps at the ends of 4 kilometers. Okay. We designed the thing in case we were wrong for pumps every 250 meters, but we never had to buy them. A lot of very ordinary calculations showed us that if we could save probably a factor of 3-4 on the vacuum system.
So you mentioned that you made the tube a lot wider for the LIGO than a typical accelerator. Did that improve the vacuum because the off-gassing comes from the walls, but the total volume gets bigger and relative to the surface area?
No, you're very close to the answer. What it is, the pumping speed of a tube, okay, goes like the area divided by the length cubed. Okay. So it turns out that if you can make the area very large, you don't have to put as many pumps on the system because the friction effectively, or the scattering by the walls of the molecular flow, is not as much inhibited by the tube if it's a larger diameter. And so, for example, no accelerator could ever live like that, have a pump only once every 2 kilometers. why the two reasons. One is they're much smaller tube. And so you can't, the resistance in the tubing will keep the pump from working properly. Okay. But the other one is that the accelerator also causes gas. In fact, when the gamma rays hit the wall, they come from the Bremsstrahl, from hitting atoms. You get heating of the walls and it makes more gas. So they have a different problem. We have laser beams in there, but they don't hit the wall. They hit the mirrors. Maybe 1 part in a million hits the wall. Okay. And so thereby don't make a source of particles that are outgassing the wall. So there are two reasons. It's better pumping speed and you don't have a source in the back.
That's interesting.
Okay, so there is one more question on the LIGO side. We found there is a statement that LIGO has been claimed to be the most expensive project in NSF's history, at least at the time when they funded it. So it says that almost more than $400 million were budgeted for it at the time, the beginning stage. So that's fascinating. And how did you and your team manage to get that financial support for the project?
The numbers, give you the numbers right so that you have them. The whole thing was proposed as at its initial construction of about $280 million. That's what the initial proposal was. And that built all the infrastructure, beam tubes, the buildings, and the detector, initial detector. And then there was another request for about 130 million. I'm not sure of this number, but it could be between 150 to 130 something for the advanced detector, which is the one that ultimately made the detection. So add that to the other part of it, which is about $50 million a year to run LIGO. And that is, when you put that all together, you wind up with a number that's close to $1 billion. And the biggest expense is the running of the LIGO for all those years. And NSF is finding that as a big problem for a lot of their facilities. How do they keep making new facilities which are better, and then the running costs are something that is eating up money that doesn't have a special source of money? Let me say, well, right now there is something called the Major Research Equipment Facilities Construction account, which is something like $400 million a year. And of that, LIGO was one of the first to use that account. Then all the other NEON, many other projects that they did, ARMA, and even the high energy. There's been a history ever since LIGO did that in 1994 of using that MREFC fund to build new things. But then what happens is as you do that, you keep putting a bigger burden on the continuing money that comes for operations. And that's something that has to be solved. As they get more and more facilities, they clearly have to shut some down which are no longer productive. And that's hard because they typically they stay quite productive. But that there is not yet a line item in the NSF budget for operations of these facilities that have been supported and built by MREFC funds. And that, I'm afraid, is something that Congress has to look at seriously because it's going to become more and more of a problem. Did I explain enough? I think that's the best I can tell you. It wasn't all in one shot. That's not the way it was. The MREFC account is what paid for each shot of doing something new. But then the running costs came out of the general NSF budget. And that's what turned out to be painful.
And